I'll start the recording, then I'll share my screen to start it off.
Mm-hmm.
And present.
All right. So first of all, thank you for everybody for attending. This is the final presentation on the work we completed on the Ware project this go around. So first, we'll start off with a quick description of the project. The end goal of the project was to produce a functional prototype that could collect and process 8 channels of EMG data. The prototype needed to be able to transmit data, store data, and collect positional data. Now, here's an agenda of what we're going to be talking about throughout the presentation. We'll start off with the breakdown of the system, then go into some schematics and final design of our PCB, talk about our mechanical enclosure, look into the final software revisions we made to finish the project, a Decode application we made. We'll look at where we're leaving off on the project, and we'll demonstrate some of its functions, and then go over some recommendations for future goers of the project, and then open up for some questions.
So here's a block diagram of how the system works. The system starts with placing electrodes on a target muscle. From here, the ADS chip interprets the signals, then transfers the data to the microcontroller through SPI. The microcontroller then takes the information, allows the user to change between 3 different modes, writing to an SD card, sending a channel over BLE, or printing it through the serial monitor. While the ADS collects the data for the position system, while the ADS is collecting data, the position system is recording the orientation of the device and the foot position depending if the user wanted to use the foot switches. This information will also be written alongside the SD card if you choose to go through the SD mode. Finally, while all this is happening, there's a 3.7 volt battery that's powering the whole unit in itself, and this is connected to a charging and protection IC, which is distributing the proper voltages along the system.
All right, so I'm going to give a rundown of the schematic and the PCB. So this part I'm not sure if it's going to record or not, but that's okay. So here on the sheet is the ADS circuitry. On the right side here, we have some digital pins that are required for the commands and as well for the SPI communication. This year's team added a mini HDMI port, which is interfaced to the 2-stage low-pass filter, which then goes into the inputs of the ADS 1298. On the next sheet, we could see the microcontroller unit, which is a Teensy 4.1. This is upgraded from last year's Teensy 3.6. It boasts a bit more functionality and a higher clock rate, a base clock rate. So with this chip here, we have, as we saw before, the ADS commands and the SPI communication, and some peripherals such as the FSRs. And on the right here, these are 3 switches directly interfaced to it for switching the mode from serial to SD to Bluetooth. This year's team also added, as we were speaking about before, the FSR foot switches. So these are 2 FSRs that are interfaced through a Molex connector, and then a Molex cable, which is tied to these FSRs. And this is just a simple voltage divider circuit to get that analog output from the FSRs. As well, this year's team changed out the Bluetooth chip for a slightly upgraded one that boasts the capability for Bluetooth 5.2 communications. This also required a JTAG connector, as we can see up here. This is required for programming the system on chip in here, which is a Nordic Semiconductor NRF 52832. So we plug in a connector to this to program that, and Thomas will talk a bit more about the programming of that later. Down here is just the IMU, the 9 degrees of freedom BNO 055. And then onto the final sheet, we have the power system. So comprised of the power system, we have two 2.5 voltage regulators. So these both output 2.5 volts. This is needed for a differential voltage supply on the ADS 1298 chip. Just before the negative 2.5 voltage regulator, there's an inverter to get that negative voltage. A 5 volt boost chip, that's to power the Nextion display. And then over here we have the charging and protection circuitry. So you'd have power coming from a wall charger or a PC going into the BQ24380, which is just an overcurrent protection IC, which is then going to the MCP73871, which monitors the battery charging and the battery output. So here we have the battery connector right here, which we have a 3.7 lithium polymer battery being connected to that. And these are some status outputs that this IC supports for charging and battery status indication. So I'll show you the PCB, the printed circuit board, with all this integrated onto it. So this year's team added a couple connectors, the Molex connector for the FSR switches and the mini HDMI port for interfacing an electrode array or an electrode sleeve. The upgraded Bluetooth chip here with the JTAG connector. In the middle here we have the ADS chip itself. And then the Teensy 4.1, which goes right on top of the power system. And we got this board printed and manufactured, and we populated it using a stencil that came with the manufacturing, and then using solder paste to go over that stencil, and it goes on all these little pads, and then placing the components one by one and sticking this into an oven. We actually used a toaster oven that was modified to, carefully watch the temperature and get the reflow profile right so that everything was soldered correctly. We ran into a couple hiccups, but we'll talk about the troubleshooting in a second.
All right, so I'm gonna show our. Let me just get my screen. Sorry. I'm going to show a little bit about the mechanical enclosure for the Wear device. So we had to update the mechanical enclosure design because we changed the dimensions of the PCB. And so we used the previous year's design as a base and just sort of made some improvements. So here I'll show the bottom portion of the mechanical enclosure. We included a battery wall to make sure the battery stays in place while the device is moving. Since it is a mobile device, you don't want everything flying all over the place inside the enclosure. The bottom half of the enclosure allows for multiple inputs and outputs that are going to be connected to the device. And then if we move over to our top piece, this is the cover of the enclosure. It's basically just made for the Nexion display to be mounted and attached to the device. Just on the back side, you have your port for some cables and access holes for the Nexion display. Then we'll move over to our enclosure. So this is what the final enclosure looks like. Now we 3D printed the enclosure at 30% density. We used a tolerance of 0.5 millimeters to account for the tolerances in manufacturing a PCB and 3D printing. We had 3 prints go through. So we had an issue with this portion right here. We didn't have enough room for a finger to go into the device to get the SD card. So we had to open that up a bit. Then on the other side, we had enough room here for a micro USB to charge and program the device. We didn't account for the insulation of the cable, so it wasn't able to fit in. So we had to fix that. And then the last air that we had was for the Nexion top. It wouldn't go into the hole, but the issue was not the design, but the way we printed it. So we reprinted the top, and it ended up working in the end. And that's it from our mechanical enclosure.
So this year specifically, as you guys know, we've updated our Bluetooth. So I'm just going to share my screen here. And this is basically the Bluetooth code that we had to use this year. This is the Nordic software. So it's a Steiger Embedded Studio. This is one of the examples with a couple modifications to suit our needs. But basically with this specific, this is all code written in C. And as you can tell, it's very intense looking and doesn't look good at all. As you can tell, also on the left, all those folders are nested libraries that are with this specific code. So changing anything would not even compile properly unless you know exactly what you're doing. So fortunately for us though, they do have a UART specific program. So we were able to actually take data from the microcontroller through UART and broadcast one channel through Bluetooth and actually get that channel on the Adafruit app, which we'll, spoiler alert, see later. So it was actually really good. So it ended up working nicely, but the code itself is very intense looking and very hard to read right off the bat, especially with our limited knowledge in programming. So handing it off now.
Thank you. Okay.
All right, so I'll talk a little bit about our code to store the data onto the SD card. So before to store data, we collect the data, open up the file off the SD card, print the data, and then close the file and clear the buffer. And that took 12 milliseconds, and it occurred every time we wanted to collect data, and it was just not cut out. We made it more efficient. So to make it more efficient, we took the data into a data buffer, and we collected 100 samples. And once 100 samples were collected, we'd open up the file once, index out a single sample, and then print it to the file. And we did that every time until all 100 samples were printed. And then we closed the file and cleared the buffer. This happened in 70 milliseconds for 100 samples. So we made it a little bit more efficient compared to 12 for one sample. So yeah, that's all for the data logging code.
Okay, so I'm going to be talking about the software for the final revision. First of all, I want to say that we are really happy to say that we're closing the project in its most stable and efficient state. I'm going to talk about some of the software fixes we made. So originally, when we first got the code, there were two glaring issues with the programming. There was two big bugs. There was this one, which was basically the program was not able to read the device ID from the ADS1298, and this would basically cause the system to not be able to write any data coming in. The way we fixed this was basically to implement a function that would just, okay, is the max channel number 0? Okay, so what we're going to do is we're going to go try to keep on reading it until we get it, then write all of our registers. Before, if we had implemented something without the function, it would take the ADS1298 register code, but it wouldn't be able to write the registers correctly. So this is fixed. The other error was the registers and the ID were all correct, but all of the data that the system was writing was all flatlining at 0. This, like the other way, we fixed with another function. So the way we did this one was basically we waited for the system to boot up, to basically wait until it was a steady state. And we said like 3 to 5 seconds to wait for the system to completely boot up. And if all of those numbers were 0 and when it was starting up, then we would say, okay, rerun it again, write those registers and reboot. And so far, like we've had absolutely no problems. And we say that both those software problems are completely fixed and it's running perfectly. So additionally, we noticed that when we first got the code, it wasn't as well commented through the entire flow of the code as we would have liked. So we did take the liberty to actually add a lot more comments in all portions of the code. So whoever looks at it next can understand exactly how the entire code flows from each point. So the final software has 2 revisions that we want to talk about also. Basically the PCB prototype and then the prototype utilizing the ADS1298 development kit. We created 2 of these because the PCB has just a few minute changes as opposed to the other revision. Namely, those are basically just the location of some pins that we have. So the buttons to control which mode you're going to be selecting and using the device with, we wanted to put those in a spot on the PCB that was a little bit more accessible. So that changed from that revision to that revision. The other thing was we took out a lot of troubleshooting numbers and troubleshooting code. We commented out in the PCB version of the software. This was basically to show that it was like the final revision, the absolute, how it's supposed to run. So we have a bit of a demo later on that you'll actually be able to see on how the program should operate and how it should look when when it's being used. Next, I'm going to be talking about the Nextion. So we didn't do all that much with the Nextion. The Nextion was quite well done from the last revision. The only thing is the scope for the Nextion. So we noticed that when the device we wanted to basically plot onto the Nextion digital display, the system did not have enough processing power to keep a real-time, good, accurate graph of all the data coming in. So we kind of we basically took out the scope. Well, like the scope operates, but it doesn't operate well. So we don't really want to use the scope. We kind of recommend for the next teams to reduce how many times the Nextion will check the data and plot onto there. This would basically allow for the processing power to be a lot reduced, and this should allow for the scope to actually show good serial data coming out and coming in through the device, and that should work. The final Nextion display features. So we have basically just you'd be able to interface the entire system through the Nextion display. So you can swap between all the different software modes, the Bluetooth, the SD card, and all that. There's feedback in each mode. Even in the serial mode, it'll say that you're in that mode and all that. It shows that it's working as intended for the SD mode and Bluetooth mode. It reports the IMU positional data to the user in real time, as well as it specifies any problems with the device if they occur. So, if like somebody unplugs the mini HDMI or the SD card, it'll alert them with a message on the display. So, finally, Hunter's about to get into a SD decode application that we use to basically convert the EMG data coming from the SD card into filtered data. We did this on the application to help, again, reduce processing power on the microcontroller and make things a little bit faster on that end. So the way that this works is pretty simple. So we get the unfiltered data coming in through the SD card, then pushes it through a couple filters, and then we get our filtered out. This has worked pretty well, and we're pretty happy with it. Okay.
All right, I'll take over.
Yes, please. Yeah.
I'll talk a little bit about the Decode application that we developed. I'll have to share my screen. And we'll just move from there to here. So the Decode application was done in LabVIEW just to give us, since it wasn't a critical part of the project, it's sort of an extra thing. We use a software that we were familiar with, so it wouldn't take too much time away from the main processes of the device. So it's basically a interface that will allow for you to convert the data stored on the SD card to readable data, so people can actually, understand what's going on with the system. It provides the ability to save data to an Excel sheet, so you can save it and review it later. And yeah, it processes data pretty quick. You see there, processed 2,000 samples in less than a second. The only thing about the LabVIEW is that we haven't figured out a way to make the data look better, but in Excel you can actually see the sample. So this is a 2 hertz signal. It's sort of zoomed in because I don't have that big of a laptop screen, but it's a 2 hertz signal. It was the data that we had on the SD card, and this is all from the Decode application. So yeah, that's the application. So I'll hand it over to Thomas.
Kevin, but yeah.
All right.
No,
So I'm
sorry.
just going to quickly talk about the current state of the device and where we're leaving off with it. So our upgraded prototype with the ADS1298 development kit works as expected, and it works with the new Teensy and the new Bluetooth modules. So that's functioning as it should be, although that PCB I showed you before has some issues with it, mainly revolving around the ADS1298 chip. So we can observe that the Teensy microcontroller unit is able to send signals to the ADS, but we're not receiving any response. It's from the master in slave out. So that's the output from the ADS1298 that sends like an acknowledgement and its device ID to the actual teensy. And when we start it up, we're not receiving any of those signals, and we've probed it and tested it with an oscilloscope, and we're receiving pretty much a flat line from the meso. So we were kind of still in the stage of troubleshooting, and we haven't completely resolved the issue, although we've provided some recommendations for the next team to look into doing some things. Right now, though, we're going to show a demo of the functioning prototype.
So this is the first video. So this is actually a picture of our prototype. So our mod board, our new Bluetooth mod board's in the back there. Everything else kind of looks familiar because it was from last year. Here I have them actually hooked up straight up to my arm, basically, and just twisting it around. I'm getting feedback in the serial monitor. So there's something's going on there, and we're getting a reading on the screen. So that was pretty cool to see, actually, with all like the hurdles that we've been jumping through. Oops, my bad. And I have a second video for you as well. This is the Bluetooth I was talking about. So you can see here we have where we can connect to it. And then I click the plotter, but I haven't hit the button yet. And then once I hit the button, you'll be able to see here's the 2 hertz signal. So like Hunter was saying earlier, we run a 2 hertz signal through a function generator for most of our testing phase. So as you can see here, here's a 2 hertz signal going through and being broadcasted over Bluetooth, in other words.
All right, so this is the final part of the presentation. It's just some recommendations for the future of the Wear project. We recommend performing further testing and troubleshooting on our populated PCB, just so somebody can figure out the main issue with it and just avoid it in the next revision. We recommend consulting with Texas Instruments on the ADS 1298. Just sort of get some knowledge on it, more knowledge than we had, and figure out if there's anything that would have caused the ADS not to function correctly. We recommend making a test bed prototype for the ADS 1298, just to allow for easier testing and troubleshooting when trying to get the ADS to function. And for future Wear teams, we recommend having a final prototype around the midpoint of the project term to allocate for time for troubleshooting. This is something that we did not do. We obviously waited, till like the end point of our project, expecting our PCB to work first try, but it doesn't always work like that. So we recommend to sort of give some time for the troubleshooting. Anyways, that's our presentation. I'd like to thank everybody for attending, and we're open for questions if anybody has any.
All right, I'm just gonna stop the recording quick too.